Hi, this is Li Xinzhang speaking, and I will use some of easy PowerPoints to help me present this topic. And here is a basic content list. And also I will add some subtitles to the video for easy understanding. The first one is the first part is definition, and the second part is about function, and the last one is two example. In the question 5 in coursework 1, this is a screenshot for the question, and we have proved that relation R is an equivalence relation by proving it is reflexive, symmetric, and transitive. And here I will briefly introduce something new, something relevant called Mahel-Neural theorem. By the definition of that theorem, there are two key words. The first one is distinguishable, and the second one is indistinguishable. In details, I will say let S and Y be strings and let L be any language. We say that S and Y are distinguishable by L if some string Z exists whereby exactly one of them strings S, Z, and YZ is a member of language L. Otherwise, for the second keywords, for every string Z, we have XZ belongs to language L whenever YZ belongs to L. We will say that S and Y are indistinguishable by language L. We can imagine that in our DFA D, let QDS be the state D is in. After reading S, if QDS equal to QDY, then for any string Z we have QDXZ equal to QDYZ. Therefore, D accepts both of them or none of them. S and Y are indistinguishable by the language of L. Here we can go back to the question 5 in coursework 1. We can easily find that the condition in this question is totally the same with the indistinguishable. Therefore, we have a new proposition for this theorem about equivalence relation, which says let L be a language and let R be a relation, and both of them on an alphabet, where S, R, Y if and only if S and Y are indistinguishable by language L, and then R is reflexive, symmetric, and transitive, so that relation R is an equivalence relation. The relation R is an equivalence relation. Let us move to the second part about function. The first one is it can be used to prove whether or not a language L is a regular, and the second one is find the minimal DFA. And the first example is about the first function, and the topic is here, and this class example is not a regular language. We will show that language L has infinitely many equivalence classes by showing that a to the power of k and a to the power of j are distinguishable by language L. We will let s equal to a to the power of k and y equal to a to the power of j and k is not equal to j. And let z equal to b to the power of k, and then we will easily find that sz is equal to a this part, and this part is not belongs to this part is belongs to language L, and however when we do the same thing on YZ, we can easily find that this part is not belongs to language of L. Therefore, we can say each equivalence class of L can contain at most one string of them of the form a to the power of j. So there must be infinitely many equivalence classes. So the language of L is not a regular language. And the second example is about how to minimize a DFA. As we can see, this is a DFA. In order to minimize it, we should draw a table for all pairs of state P and Q first. For example, like this. like BA or CA. And the second step is we need to do is mark all pairs where P is final state and not Q, but not Q. For instance, we can see both A and B are not final state. So in this position, we don't need to do anything. However, let's see the pair of A and C. C is an final state, but A is not a final state. So we have to mark here. After we go through all the pairs, we will get a table like this. We will get a table like this. And next, we need to do something on the unmarked pairs like BA or DC. And what we need to do is check like this. For example, the BA. With the transition function, we input 0, we can find that when input 0, B's go to A, and when A input 0, go to the B. So we got AB here, and as we can see, AB is unmarked, so we don't need to do anything. However, see another example, FA. So when the input 1 in the F state, we got a F, and when we input 1 in the state A, we got a C. And so we got a FC here, and we can easily find that FC is marked. So because FC is marked, so we have to mark FA too. And after we go through all the unmarked pairs, we got a table like this. This is the final table. And the last thing we need to do is about is combine uh is combine all the unmarked pairs and made them a single state in the minimized DFA. So we will do the thing like this. As you can see, the unmarked pairs is AB, AB, DC, EC, and ED. So AB is pair, DC is a pair, and EC is a pair. EC is a pair, and ED is a pair. And then we can easily construct or minimize DFA like that. AB, CDE, and that is the final answer. Okay, and this is the end of video. Thank you.